Okay, here we are. Let's take a look at where we are. This is going to be part 2 of volcanoes, explore number 2. And I want you to take a look at the text. What is it that we're trying to understand? It's that part in green. Where do volcanoes come from? Okay. Now, your English teachers have taught you reading strategies. So one of the first things you do, think about the question, what do you know? And also, what do you anticipate that this text is going to share with you? Okay. Now, as we go down, let's take a look. We're going to scan the article. We can see these subtitles here: volcanoes at divergent boundaries. Okay, so the question was, where do they come from? Apparently, they appear at divergent boundaries, and they're going to give us details here. I see this picture here, mid-ocean ridges. And if you recall, mid-ocean ridges, like the mid-Atlantic ridge, that's where seafloor spreading is occurring. So that is a boundary, a divergent boundary. And you probably can infer here that there's going to be a volcanism down there in the middle of the ocean, on the ocean floor. We've got a nice simulation, formation of volcanoes, and these are there for your benefit. So make sure you click on that. If you're trying to figure out how to do better, you've got to take advantage of the resources that are provided. Oh, look at that, volcanoes at convergent boundaries as well. Apparently, there's going to be, you can have volcanoes where tectonic plates converge, and you should already be thinking about your past learning. You can have oceanic plate converge. You can have oceanic and continental plates converge. You can have continental and continental converge, right? And then it looks like we also have another region where volcanoes can occur. These are hotspots. You may recall from past conversations with science teachers in your science classes what hotspots are. Perhaps not. Maybe this is the first time. So it certainly seems like just in our preview of this page, they're going to address these 3 general areas. And a lot of interesting structures that we'll be hitting here. Okay, so let's go back up to the top and let's dig in. So I'm going to go ahead and pull out my pen, and we're going to go ahead and draw our lines. And I'm just writing today's date because I'm doing this in the evening. But it is 9:28 that I'm doing these notes. You can write 9:29. That's fine. And let's see, today is Thursday for myself, but you might be doing this on Friday, and that's okay if you write Friday 9:29. That's perfectly fine. Draw your Cornell margin notes line there because you want to put information on the side that's useful to you. And our essential question, where do volcanoes come from? Question mark. Okay. Now, I would normally in our class, I may suggest what do I already know and what I know. And I might suggest to you that you actually take a little moment and write down what you know. After we're done with these notes, you're going to know a whole lot more. But you can pause this video right now and just write that down, okay? And you never know. I may actually look for these when I do your notebook checks. Okay? All right. All right. Now that you've written down what you know regarding this, let's go ahead and start with Roman numeral 1. Okay? Volcanoes at divergent boundaries. Now, of course, I want you to read these paragraphs after we've taken the notes, but hopefully this will help you just kind of front load and understand more what you are going to be reading, okay? As we take a look here on the left-hand side, volcanoes on land receive most attention because of their proximity to human communities. However, most volcanism occurs in the ocean along divergent plate boundaries. That's an interesting point here. Let's put down A. Most volcanism, that means volcanic activity, occurs in the ocean along divergent plate boundaries. Okay. So if you're a visual person, you may want to just simply draw an ocean, right? And on the ocean floor, you may want to draw a plate boundary. And you may want to just show that this is divergent and this is divergent. These are diverging plates. And apparently, from what we're saying, we must have a lot of volcanism. So you have a lot of magma that spews up in this region here, okay? And I think that's kind of what they're saying. So the visuals might be helpful for you. Now, looking in yellow here, a mid-ocean ridge system consists of a series of volcanoes that form along a spreading center. So that's a term you should be aware of. Let's scroll here, letter B. Mid-ocean ridges. These systems consist of a series of volcanoes that form along the spreading center. Okay. Now, when the red here, you notice I'm using different colors for our highlighting. This gets kind of into detail. As the plates move apart, mantle pressure decreases, and the magma wells up from the Earth's interior. The heat from the magma also makes the surrounding crust less dense. As a result, the crust rides higher on the asthenosphere, accentuating the height of the mid-ocean ridge system. Okay, so what can we, this obviously is related to mid-ocean ridges. So let's go ahead and put this as number 1. As plates move apart, the mantle pressure decreases. That's an important idea. Mantle pressure decreases. The heat from the magma also makes the surrounding crust less dense. Okay, so let's think about this. We're talking about density. As the plates move apart, mantle pressure decreases. What does that mean? Well, if the pressure decreases, then is it possible for that magma to expand? If it was under pressure and as it moves up through the crust, there's less pressure. Is it going to be able to flow easier? Is it going to be able to flow faster? Maybe these are some thoughts that we should put out here on the side. These are kind of our thoughts to ourselves. Does magma expand? Question. flow faster? Question mark, because it is saying that magma is moving through a region that all of a sudden has less pressure. Okay, so you're trying to be an active thinker in your note taking. Item number 2, the heat from the magma also makes the surrounding crust less dense. So the rising magma heats the surrounding crust, and what does that do? Making it less dense. Making it less dense. And as you know, anything that is less dense than its surrounding material is going to rise. It becomes more buoyant. Therefore, it lifts or rises. It becomes more buoyant, right? And that causes the ridge to ride higher, it says here. The crust rides higher on the asthenosphere, accentuating the height of the mid-ocean ridge system. Okay. All right. Now the green highlights mean maybe a new idea. Magma source generally has a homogeneous composition that is low in silica, aluminum, and water. All right. So this is going to be a new idea. So let's go ahead and write this as letter C. And what do we mean when we say magma source? Well, magma is melted rock. So they must be referring to the source rock. Magma source generally is homogeneous. That means it's made up of a uniform type of material, is a homogeneous composition. And what does the composition consist of? It is low. These are probably things you want to say. Low in silica, low in aluminum, and low in water. It's low in water, okay? The lava has a low viscosity, flowing easily and producing relatively quiet eruptions. As magma reaches Earth's surface, it sticks to the wall of the ridges and cools, forming basalt. Okay, so we're talking about these ocean ridges, and we want to say that this stuff, the characteristics of it, again, we're at the bottom of the ocean, characteristics, because that's what they just described to us, right? They have low viscosity. That means they're not very thick. They flow fast. B, they flow easily. Flow easily. And C, these are relatively quiet eruptions. Quiet eruptions. Okay. And what can we say about this? Characteristics. Number 2, we can say that it forms basalt. This is a type of rock on the ocean floor, which is heavy. It's dense, right? And it's dense and heavy because it has iron and magnesium, if you recall from some of your past studies. All right, so let's go ahead and just erase that mark that I just did. And let's just scroll here. So mid-ocean ridges, we can see a number of mid-ocean ridges, interconnected mid-ocean ridge systems from the boundaries of many tectonic plates. You got the Mid-Atlantic Ridge. Let's go here. We got the Mid-Atlantic Ridge. We have the East Pacific Ridge, the Pacific Antarctic Ridge, the Southeastern Indian Ridge, the Southwest Indian Ridge, the Central Indian Ridge, and we have the Juan de Fuca Ridge. Okay, so these are some terms here. Okay, let's kind of keep going here. And under the next text here, mid-ocean ridge systems snake around the globe. Several interconnected mid-ocean ridge systems have been identified. That's just what we looked at, right? So maybe we can put down letter D. We'll call these mid-ocean ridge systems. And examples of these are the EPR, which is the East Pacific Ridge. We have the Mid-Atlantic Ridge, MAR. We have the third example they provide in this paragraph, the Southeast Indian Ridge. Okay, so make sure you read the paragraph, okay, because I've obviously read it and I'm just drawing your attention to some points, but you need to make sure to read it for the details, okay? Okay, well, that takes care of volcanoes at divergent boundaries. Now let's talk about volcanoes at convergent boundaries. So let's take a look at our organization. Number one was volcanoes at divergent boundaries. So Roman numeral 2. We got our line. Roman numeral 2. Volcanoes at convergent boundaries. All right, these are where one plate approaches another plate. They converge, right? Okay, these are convergent boundaries. And it's okay to do your notes and try to understand. As the plates converge, they produce a unique feature called a subduction zone. So this is an important point that you are aware of already. Subduction zones form. And they usually have a trench associated with them. Trenches form at these subduction zones. And as you can see here, as I've read further down in the paragraph, the addition of water and ocean sediments change the composition of the surrounding magma. Okay, so as that magma is being produced, it's being contaminated by ocean water. It's being contaminated by sediment, right? Because sediment falls to the bottom of the ocean floor. And this produces a more buoyant plume of magma that travels upward. This plume melts through the overriding crust as it moves towards Earth's surface. So what can we say? We know that subduction zones form, trenches form, and we know that plumes form. These are these kind of rising magma bubbles. We'll just say blobs of magma. Now, what's particular about these plumes is that they are very buoyant. A buoy is something that floats on the water. If you've ever been out to the ocean or a lake, you might see that you have those things floating out in the water, and they call those buoys. They're very buoyant. They float upwards. They float up. Why are they very buoyant? Because of water and sediment contamination. Um, because of water and sediment mixed in. And we could say contaminated, and that's not necessarily saying something is bad. We're just saying that something has gotten mixed with it. Okay. As the plume melts through the continental crust, the composition becomes even richer in silica. Okay, so this is interesting. It melts the crust above it as it rises. And as it melts the crust, it's going to become even richer in silica. Becoming rich in silica. Remember, silica, sand, right? I mean, that's really the silica is a chemical compound that we find inside sand. Rich in silica, okay, which is what? Very viscous, very thick. Very viscous. This is a key idea here. And, you know, if you've ever cooked sauce in a pan on your stove, like tomato spaghetti sauce, and it's a thick tomato paste or something really thick, and you've got it on high, you know it's getting hot, and then all of a sudden it just starts to bubble, but it like bubbles like, and it explodes, and it like splatters all over the place. That's the way this is. When things get really thick and heat builds up, when the heat, the air bubbles break through, they kind of pop, they explode, right? Therefore, explosive. This is an explosive type of lava, okay? Explosive eruptions occur with this one. Unlike in the ocean, remember in the ocean when you had ocean plate versus ocean plate, and they were diverging, they had a low viscosity and they were relatively quiet sort of eruptions. But these kinds on land are explosive. Okay. So compared to the ocean continental convergence, the silica content of magma produced at ocean convergence remains low. Versus ocean. We're talking about oceanic plate and oceanic plate, which is low in silica. And so it's not explosive. All right. Going down here, a low viscosity allowing gases to escape to the atmosphere, which enables these volcanoes to produce quieter eruptions that release large volumes of lava. So they're talking about the ocean. Okay, so we're talking about, let's go ahead and write this down here. We're talking about ocean convergence. The silica content is low. It's only slightly enriched in silica. It has a low viscosity. They're going to produce quieter eruptions that, number 5, release large volumes of lava at Earth's surface. Okay, these are the characteristics of ocean convergence. This is the type of volcanism you get. Okay. All right. And then we have a third type. This is going to be Roman numeral 3. So we're going to draw our line down here. And we have Roman numeral 3, volcanoes at hotspots. As you see in green, not every feature on the ocean floor can be explained by plate tectonics. Non-divergent ridges and volcanic island chains can be found outside the vicinity of plate boundaries. Okay. Not all volcanoes occur at boundaries. This brings us to the next idea, hotspots. Hotspots. What are hotspots? A relatively stationary plume of magma, a relatively stationary plume of magma that scientists think originates in the mantle core boundary. Most active hotspots are found underneath the Big Island. The most active in Hawaii, you find these things. Reunion Island, the Galapagos Islands, and Iceland. Volcanoes over hotspots expel massive amounts of lava that contain low silica. That would, I think, make sense because divergent plates on the ocean floor also have low silica content. Conversely, hotspot volcanism on a continental crust is often violent due to the addition of silica from the continental crust. So you have this type here versus this type here, okay, on continental crust. Okay, so let's write this down here. Okay, this is good. Letter A, hotspots. On ocean floor. Have low silica concentrations versus on continental crust. Which have high silica concentrations. Which one's going to be the most explosive? Most explosive. Okay, similar idea that magma is being contaminated by silica from the crust, and that silica is very viscous. So your magma is going to become more viscous as well. Okay, let's see here. Hotspots remain relatively stationary over long geological periods. As the tectonic plates move over the hotspot, the magma plumes melt through the lithosphere. So what happens is you may have the, maybe we should draw this. We've got a plume of magma is rising. Call this a plume. And then we have the crust above, and the plume melts the crust above. Okay. Now, the crust is, let's say, moving, right? The crust can move. And so we could say that this is going to melt through and create your